I think we're ready for me to introduce you to our last speaker. And our last speaker is a very familiar face. Especially if you remove the beard, you will see quite the familiar face. Ken, with a raise of a hand, raise your hand if you have participated in a course taught by Stefan, please. All right, there's a few students. So Stefan, he is currently a CTO at CTO Bank, and he is also a beloved developer here in Bulgaria and a teacher at the Faculty of Mathematics and Informatics. And something quite interesting is that this here right now is going to be his first talk for the last 2 years. So this is, yeah, we're making history. Please, a very big round of applause for Stefan Kanev.
Can you hear me? Raise your hand if you cannot hear me. Very funny. Anyway, what I'm going to try to do today is answer 3 questions for you. 1, what is machine learning? 2, what's all the fuzz about and why now? And 3, if you want, how do you get into it? How do you become a machine learning engineer? And first, I need to make a very, very, very big disclaimer. 40 minutes is not enough to give this subject, just like even start covering it. If you take an introductory course, just the basics, just the overview, is probably going to take more like 4 hours. So I'm not going to attempt to paint a full picture here. Instead, I'm going to try to paint pieces of that picture, some in a lot of detail, some very broadly, and let your imagination connect the dots. I'm also going to be very inaccurate in some areas or gloss some things that are actually important, just for the sake of time, not because I don't know them. There are a lot of them I don't know either, but anyway. For example, I'm going to pretend that supervised learning is the only type of machine learning, although there are a few more. I'm going to pretend that you need to split your data into 2 parts. Actually, you need to do it in 3 parts. And I'm going to mention the word regularization twice. Once now and once in passing, even if this is a pretty key concept. So, without further ado, what is machine learning? It's essentially using data to discover how to answer a specific question or problem, as opposed to writing an algorithm for it. And let me give you an example. Suppose you have a bunch of pictures. Some of them are pictures of cats, some of them are pictures of dogs. And you want to write a program that takes a picture and tells you whether this is a cat or a dog. Now, in a non-machine learning world, you can, and I really don't know how you can solve this problem, but if you're very smart, maybe you can figure something out. I'm not that smart. Maybe like apply some filters, try to detect the shape, look for key features of cats and dogs like pointed ears and whatever. And this sounds very, very complicated. So instead, you want to do something else. You want to go, hey, Mr. Computer, here's like a few million pictures. Those are the cats, those are the dogs. Figure out the difference and learn how to tell one from the other. So next time when I give you a picture I've not given you before, you can tell me whether it's a cat or a dog. And that's what essentially machine learning is, solving problems like that. I'm giving an example with images, but it does not need to be an image. It can really be anything that's a matrix of numbers. Images are matrices of numbers by default, but you can transform a lot of other data into a matrix of number. Any tabular data will do fine. To train a machine learning algorithm, you can also work with text. There are cool ways to transform text into numbers. You can do sound, you can pretty much do almost anything. Here's a different machine learning problem, and is the one about figuring how much does a used car cost. So you have a table with the make of the car, the model of the car, the year the car was produced, the mileage, and the price. And this is also something you can train machine learning for. you can use data to figure out a way to decide how much a used car is going to cost. Now, just to repeat this point, if you're a used car salesman, you've probably seen a lot of cars and know how they're priced, and maybe you have some internal rules and you can make that call by yourself. But the whole point is to do this without any expert knowledge, just the data. This table kind of gives you the layout for machine learning problem. What you start with is a bunch of data points. Each row here is a data point that's a used car and its price. And you call the first 4 columns features. That's the things about the car that you know. And you call the last one the label. That's the answer of the question you want to answer. And what machine learning is essentially finding a function, let's call it f, from the features to the label. And every machine learning algorithm out there in supervised learning does that. So that's essentially the formulation of the machine learning problem. You have a bunch of x's, a bunch of y's, and you want to find a function that maps the first to the second. Within machine learning, there are 2 different types of problems. One is called regression, the other one is called classification. So regression is when y is a continuous value, like the car price, and classification is y is one of a predefined set, cat versus dog, or spam versus not spam. And that's about it. So when can you use machine learning? I mean, it like gives you a big promise. You don't need to know the details. It can solve your problem. But when can you use it? First, you need to have a lot of label data. That is not just the data, but also the answer of the question you're looking for. Not just the cars, but also their prices. Not just the images, but whether they're cats or dogs. Second, you need to have signal in that data. There needs to be some correlation between that data and the answer. And finally, there needs to be a known algorithmic solution. Because if you already knew the algorithmic solution, you don't need to do machine learning. You can just do the algorithmic solution. We know how to compare 2 numbers. For example, we don't need to do machine learning for that. And if you look at the field today, you can kind of split it into subfields, if you will. One that's neural networks, also called deep learning, and one that's everything else. I'm going to refer to it as classical methods or statistical learning. And I'm going to try to cover both today. By the way, that's an XKCD that illustrates the process of doing machine learning. You have 2 guys here, and yes, I'm assuming gender. That's how he draws men. And one says, so this is your machine learning system. And he says, yes, I have like a big pile of linear algebra. I put data in and then collect the results out there. But what if the answers are wrong? Well, you just like steer it a bit until the answers start looking right. And that's fundamentally what the process looks like. So let's take a look at our first machine learning algorithm for today. It's something called linear regression. And remember, we have a bunch of x's and a bunch of y's, and we're looking for a function that maps one to the other. So how do we apply linear regression, which is a specific machine learning algorithm? First, we assume that f has a specific form, and the form is this. Essentially a linear combination. So it's not any odd function. It just multiplies each feature by a number, and it's a constant, that number. Adds another number, this one here, and then this is your function. That's what linear regression does. And what linear regression needs to do after that is to estimate those gray values here, which are also called parameters. And now let's try to visualize this one-dimensionally. So you have a bunch of data here. On the horizontal axis, you have the feature. It's only one feature. On the vertical axis, you have the label, y. It really doesn't matter what the numbers are. The whole point is that linear regression looks for a line that has the minimal error that will be able to best predict the value of y based on the value of x. Now, this is the simple case with just one feature. Normally, we have many features, like our used car example had 4. So we get into some multi-dimensional shenanigans that are pretty hard to illustrate. You can maybe have a bunch of intuition about what happens when you have 2 features, and maybe you can visualize it in a 3D graph. But when it gets more than that, the math kind of works out, but our intuition as human beings is not that good. But anyway, back to the function. We're looking for a function like this, and how do we find the best parameters? The best A0, A1, A2, and so on. The first question we need to answer is actually what does it mean for some parameters to be the best parameters? And the thing we need to do is to define an error measure. So given any set of parameters, we can calculate the error for those parameters, and then the problem we're trying to solve is finding a set of parameters that has the minimal error. That's what you do. And let me again try to give an example. If this is your linear regression, and the red dots are the actual data points, the green dots are going to be the errors. So here is going to predict 5, but actually the value is 6, and there's an error of 1. So how do you calculate the error for the set of parameters? There are multiple ways. We're going to pick something called root mean squared error, which is really not important to understand what this formula does. It essentially takes each green bar, squares it, gets the average, and then takes the square root. But the important thing is you have a number that tells you for those set of parameters what is the error, and then you're trying to find the best set of parameters. And yeah, let me repeat what we did here. We made an assumption about what our function is going to look like. We defined a measure to determine how well this function performs. And finally, we need to figure out how to minimize it. So in this particular problem, the error measure happens to be something called a convex function, which essentially has a minimum somewhere, and then it grows in the other 2 directions. And when we have this setup, it's pretty straightforward to find the minimum of a function like that. And the way you do it is by something called gradient descent, which, by the way, sounds like a name of a really cool grunge band, but actually it's an algorithm. And the way it works is you pick any random point, you calculate the derivative in that point. If it's positive, the function is growing. If it's negative, the function is the reverse of growing, decreasing. And you figure out like which way to go. You step a bit in the direction in which it is decreasing and repeat the process. It kind of looks like this. The reason I'm showing this is because it's a very like brute force algorithm instead of something sophisticated and mathematical. And you end up doing that a lot in machine learning. Now, what's the fine print? Although linear regression sounds quite simple, it's very, very applicable. You would be surprised how many problems it can solve fairly well. Specifically, when you get very multi-dimensional, your intuition might be that the algorithm is simple because it's linear, but actually, things just work out. Secondly, it can also work for non-linear functions if you transform the features a bit, which we're going to look into later. You don't always need to use gradient descent. There's an exact solution in some cases, although it does not work in other cases, and it does not work when you have a lot of data. But gradient descent is used in a lot of other places in machine learning, so it's worth mentioning. And finally, we did happen to choose an error measure that's convex, which meant it had 1 global minima. But in some case, you might end up with an error measure that has multiple local minima, and then gradient descent does not work right out of the box, but there are some tricks you can do in order to find the global minimum of the function. And fundamentally, that's one of the most basic methods. There are some that are much more powerful. Now, you can take linear regression and you can apply it to classification problems. And that happens with the help of this function called the sigmoid. Again, you don't need to understand the expressions up there. The only thing you need to see is that it kind of maps all numbers to something between 0 and 1. And there's like a boundary somewhere that's gonna be like 0.5, and then the more you go in one direction is going to be 0, the more you go in the other direction is going to be 1. And you can use this function to reduce linear regression to something you can use for classification. Basically, this is the shape of the function you're looking for now. It just has the sigmoid here. The error measure is a bit different, but we won't get into those details. Whenever it gives something close to 0, we take it to mean one of the classes, for example, not spam. Whenever it gets close to 1, we take it to mean the other class, for example, spam. And confusingly, it's called logistic regression. I say confusingly because it's a classification algorithm, but it's called regression. The logistic makes sense because the sigmoid is also called logistic function. And anyway, let me rehash what we did. We're looking for a function that maps some data to some values that we know in advance. We made an assumption that this function is a linear combination, a fancy term for something very simple. We multiply each number by a different number and sum them. Then we defined a error measure, particularly the root mean squared error. And finally, we tried to optimize the whole thing via gradient descent. So what you're looking at here is essentially the template for every or almost every machine learning algorithm out there. And it's always the same thing. You assume a function shape, you pick an error measure you're trying to optimize, and then you use some means to optimize that error measure. And that's what machine learning is basically all about. Maybe you've heard this talk that if you're talking to investors, it's AI. If you're talking to the world, it's machine learning. And if you're talking internally, statistics. And there's a lot of truth to that statement. So let me quickly show you two more methods, different classical machine learning algorithms. One of them is called a decision tree. And you might have seen a decision tree outside of the context of machine learning. For example, here, say, decision tree about whether you should write a blog post or not. Do you understand it? No, don't write a blog post. Do you feeling tired? Yes. Do you have any tea nearby? If you do, and I guess they assume you also drink it, write it. If you're tired and there's no tea, don't write it. That's what essentially a decision tree is. Here's a different example. It can be a bit more complicated. Like whatever, you get the idea. And here's a third one, and I'm going to let you stare at it until I drink some water. Anyway, also very relevant to the subject. By the way, because I really don't have enough time, I've removed most of my stupid jokes. If you miss them and we have time for questions, you can ask me for a joke. Cool. So essentially, there are machine learning algorithms that are able to infer a good decision tree for a piece of data. They kind of find a way to split the decision making. Can be if it's here and here is this class, otherwise it's that class. There's a lot of math, well, not a lot, but there's some math under this, and we won't get into it. And finally, there's something called the random forest, which is when you train multiple decision trees and you constrain each tree. For example, you train each tree with a subset of the features. And then finally, you take a majority voting. And that's actually very useful in practice. And finally, this is the simplest machine learning algorithm ever. It's called k-nearest neighbors. And basically, you just store the data set somewhere. And whenever you get a new point, you try to find the k-nearest points, see what the label for them is, and take the majority. For example, if you pick a dot here, the 5 closest are going to be blue. So I'm saying blue for a dot here, red for a dot here. And for this particular dot, you can see that like There are 4 red, 1 green, so it's probably red. Despite being very simple, it's actually useful in practice as well. Not everywhere, but there are some problems that can be neatly solved, and it's very easy to apply. You don't need to be a machine learning engineer or a data scientist to apply this. Cool, so let's move on into another part of machine learning called feature engineering. Now, as I mentioned in the beginning, you have to have your data in something that's like roughly a matrix of numbers. And the process of taking whatever data you have somewhere, like some logs or some images or some sound waves, and transforming them to something you can use in machine learning is called feature engineering. That's a super important part of the process, and that's where you spend most of your time. Just figuring how to convert your data to something you can feed to machine learning. Here are some examples. You can have like some color values here. They're not numbers. So one way to turn them to numbers is something called one-hot encoding, where you have 3 columns, 1 for each number. You have 1 if the number is the one in the column and 0 otherwise. This is called one-hot encoding. Another thing you can do is transform the features. For example, you have some x here, and you can add the square and the natural logarithm. And that's also called feature engineering. By the way, that's the approach you can take to use linear regression to discover a function that looks for something more complicated. Or you can like transform text. And this method is called bag of words. Essentially, the columns are all the words in your vocabulary. And it's 1 if the word is present in the document, and 0 if it's not present in a document. Is the most basic way of encoding text. There are more complicated, but it's still useful. For example, those 2 documents contain both Nigerian and Prince, so they're likely spam. And this one contains just Prince and cat, but not Nigerian, so maybe it's not spam. Maybe it's Broadway music or something. And yeah, this is called bag of words. So, and here's the interesting bit. If you're using classical statistical methods, you end up doing a lot of feature engineering. If you go into deep learning, however, neural networks can figure some of the features for you. And that's one of the reasons that they're so interesting and so hot right now. Let's look into another thing. As I mentioned, I'm just going to paint pieces of what machine learning is. And this is once you've trained a model, how you determine whether it's a good model or a bad model. And it's not that trivial. So essentially, we're looking for models that generalize well. This means that if you give them some new data they have not encountered before, they tend to give you the right answer. However, it's really, really common to have very good performance on data that the model has seen and very poor performance of new data that the model has not seen. This makes the problem of evaluating how good is a model non-trivial. And in order to understand that, it's worth knowing what overfitting and underfitting means. Very basic machine learning stuff again. So this one illustrates it pretty well. If you look at the middle, here's some data, and there's a pattern in it. It's this, kind of follows this line, whatever, or this curve, whatever that curve is. But you underfit when you try to apply a very simplistic model on top of it. For example, this linear regression here does not represent the data at all. And you overfit when your model learns something very, very complicated that matches the data quite well, but it's not like fundamentally the underlying pattern, like this one here. Here's another example. Here the problem we're trying to do is separate the one class from the other, the circle from the cross. Here we're underfitting, because as we can see here, probably the solution we want is upper right corner is circle and the rest is axis, and those 2 are outliers. And here we're overfitting. is learning something very complicated that accurately captures all the data you used to train, but maybe it's not the right model for you, because maybe you think that the point here is a circle, and this X is just like an outlier. So that happens very often, and because of this multi-dimensionality thing, it's very hard to visualize your data most of the time. So there's a way to figure out whether you're overfitting or underfitting, and it is you take your data and you split it. Damn it. Technology. You take all your data and you split it into two parts. You use one part here just for training, and the other part to verify the model. So this data here you don't use to train your model. You use it later to verify whether your model is underfitting, overfitting, or just right. Whether you split 50-50 or 80-20 is a different complicated question that I do not want to get into. But here's how you look at the results. If your accuracy on both the train and the test set is low, then you're underfitting. If you have very high accuracy on the train set and poor accuracy on the test set, then you're overfitting. And if they're like kind of the same and kind of high, you're where you want to be. Your model is fine. And there's maybe a more intuitive way to explain this. A model will underfit when it's not able to learn the signal in the data, like the linear regression that did not see the curve, and it's overfitting. Do excuse me. And it's overfitting when it learns the noise in the data, like the very curvy line that picked every point but was surprisingly noisy. So when you're, and I'm just going to go through this quickly, when you're underfitting, it can help to add more features, it can help to reduce the data, it can help to try a more powerful model. When you're overfitting, you can remove features, you can add more data, or you can try a less powerful model, or use regularization, which I said I'm going to mention only twice. If you don't make the connection between this and the previous stuff, don't worry. I'm just trying to paint you bits of the process. Again, 30 minutes are not enough to get every detail. And finally, let's look into neural networks, aka deep learning. So if the other stuff is hard to explain in a short amount of time, this one is pretty impossible, but let me try. They are inspired by the way we currently think the brain operates. And the wording here is important, the way we currently think and inspired. It's by no means a simulation of a brain in a machine. Nothing like that. It shares some terminology, but like a neuron, but it's something completely different. And finally, comparing machine learning and biology is not a good idea. So, fancy name, some inspiration for biology, but by no means a simulation of brain in a computer. And what it essentially does is it puts a bunch of linear regressions together, one after the other. That's what a neural network essentially is. And let me illustrate it with a colorful chart. You have your three features here. And then there are 4 linear regressions that output this hidden layer here, which you can think about as 4 new features. Then there are 4 more linear regressions that output this hidden layer here, number 2. And finally, there's a final linear regression that outputs the, well, output. So this is what the machine learning is, essentially a bunch of linear regressions piped together. Here are the features, here's the label, and then you have some interim results accomplished by linear regression, essentially. The reason I say essentially, and let's not get technical, is because you need, if it was just linear, it's kind of the same as a single linear regression. So you need to introduce some non-linearity in the whole thing. You need to use a function at each layer called an activation function. We've already seen something that can be used as an activation function, the sigmoid from earlier. So it can be a bunch of logistics regressions piped together. But there are other alternatives. If you didn't get that, don't worry, not that important. And finally, you can think about the hidden layer, like some features that the whole training process is discovering from the previous layers. And that's kind of how you can do stuff with neural networks that don't need feature engineering. Because the neural network can figure out some features for you. Now, whether those features would make sense for you as a human being or not is a different question, but it's one way to think about what's going on. So yeah, maybe the first layer here is the cat picture and the dog picture. The second layer is figuring out some basic shape. The third layer is figuring out more complicated shape, and then here can be used to figure out whether it's a cat or a dog, or something like that. The thing I covered up to now is something called a dense layer, or a fully connected neural network, but there's also a bunch of other things you can do. There's something called a convolutional neural network, which essentially moves a filter, like a 2D filter, through every pixel of the image and calculates the result. A filter is a function of the pixel and the nearby pixels, put it simply. There are recurrent neural networks that kind of remember state, and they can be used for sequence, like human speech, sounds, and so on. And finally, there are a bunch of other things you can do in between that I'm not gonna get into because it gets very complicated. But the whole point is that when you try to build a neural network, you have to choose how many layers you have, how does each layer look like, how many neurons it has, and so on and so forth. And that's referred to as architecture. So in the neural network we've seen, so far the architecture had 2 hidden layers, each with 4 neurons, or something like that. And this is where it gets really interesting. Now, architectures can be pretty complicated. So here's a picture of a fairly straightforward architecture, the LeNet5 neural network. And it would take me at least an hour more here to explain how you can read this diagram here. But that's not the point. That's not what's important. The important is, 1, it can get pretty complicated, and 2, you don't need to understand it that well because you can use somebody else's architecture verbatim, or you can change it a bit to accomplish what you want to do. And there's actually something called transfer learning, which is pretty exciting. And let's say you have somebody like Google who has millions or billions of images, and they train a neural network to determine one of 8,000 classes in it. Is it a fire hydrant? Is it a traffic light? Is it a crosswalk? All the stuff you have seen on those captchas. And they have like a huge amount of images they can use to train that neural network, like millions or billions. And it recognizes 100 classes that are known in advance. So they can give you that neural network, the trained one. You can remove the last few layers. You can put something else there. And then you can use it to train for some new classes that you have. For example, you want to recognize cat versus dog, and the original 1,000 classes do not include cat versus dog. And you can also do it with a much smaller sample size. Instead of billions of images, you can maybe do it a few thousand. And that's called transfer learning. And the really cool thing about it is that it's a very good way to bring machine learning in the hands of non-specialists. I had friends who did not know anything about machine learning, but could solve an actual problem in their day job by using transfer learning. And some of the tools Apple and Google gives to mobile developers today actually leverage that. So let me rehash the high level of deep learning. It needs way more data and way more powerful hardware because calculation is way more complicated, and also it tends to overfit a lot. On the bright side, it can discover some pretty complicated functions, like figuring out whether an image is a cat or a dog. It's really hard to understand. It's really hard to pick up and start training neural networks from the scratch. And on one end, if you're just like a one-man band or a very small team without a lot of resource, it's pretty much harder to apply than statistical models for those reasons. But on the other hand, it's way easier to leverage other people's work. And that's where I see neural networks going in the next few years, kind of commoditizing machine learning so non-specialists can apply to problems they have a bit more freely. Because the statistical learning methods actually require you to learn quite a lot. Cool. That was my overview of machine learning. Essentially, hope stuff made sense and hope you saw some bits and you started connecting. Now, why is it relevant now? We've always had problems where we did not know an algorithmic solution and we wanted to solve. That was true in the 60s, that was true in the 80s, that was true 20 years ago. What changed to get all the hype today? And essentially two things. And they're very obvious in hindsight. First, we have much faster hardware. Probably you did not have the computing power you need to train a more complicated neural network in the 80s. Today you do. And the second thing the change is that we started having way more data, with everybody getting into the internet, signing up for Netflix, and so on. We have massive data sets we can use to figure out how to answer questions on data versus on expert knowledge. And honestly, that's about it. That's why it's popular today, that's why there's all the hype, that's why people go into it, and that's why people use it to solve problems. So, final one. How do I get into machine learning? The very first question I need to answer is, do you need to know mathematics? And the answer is a bit complicated, but long story short, in order to start, you need a little. In order to get efficient, you need more. You definitely need to know some linear algebra and statistics in the end, because otherwise it's very tricky to understand what the hell is going on. And I've also found that calculus occasionally helps, at least me, to understand some stuff. But you can definitely start without any advanced understanding of mathematics, but eventually you would need to learn that. And by the way, don't stop your life to learn mathematics and then machine learning. You can pick up mathematics as you go. The second thing you need to do is learn a programming language that I find very unpleasant and horrible, called Python. The reason I hate Python is not machine learning related. I actually used to teach Python in a previous life, but it's a very annoying language to me. Anyway, and it has a bunch of libraries. Actually, it has all the libraries you need. Now, there are some other languages that you can use, like R, MATLAB, and so on, not worth learning today. 13th of October 2019, Python is all you need. You can maybe explore R if you have a lot of extra time and like to cause yourself pain, but apart from that, Python is fine. Those are the libraries you need. Jupyter is something that gives you a notebook, which is a cool way to essentially interact with code, see the results in more interactive form, maybe draw some charts, maybe have some interaction. If you have seen notebooks in Mathematica, it's kind of similar. Generally, when you're doing machine learning, you're trying to visualize stuff all the time, and that's why people tend to use Jupyter a lot. NumPy and Pandas are your basic data science libraries. NumPy gives you fast matrix multiplication for pretty large data sets. Fortran underneath, by the way. And Pandas gives you a data frame, which is kind of like a cool interface to work with a table of data. Scikit-learn is where all the classical methods are. You'll find your linear regression there, your random forests and decision trees, your KNN, your support vector machines, and so on. And finally, for neural networks, you can either use TensorFlow or PyTorch. And if you use TensorFlow, there's something else you need to look into called Keras that makes the interface better, but that's about it. TensorFlow is very bare bones. Which one you should pick, I really don't know. You kind of need to learn both today if you're going into deep learning, because half of the resource is TensorFlow, the other half is slowly going into PyTorch. And yeah, I don't have a dog in this fight. Cool. So how do you start learning otherwise? The first thing I'm going to recommend is the courses of this gentleman, Andrew Ng, in Coursera. He has one course on machine learning, one course on deep learning. The deep learning is five times bigger, but he explains the fundamentals pretty well. If you're looking for very high-level books, that's going to paint you a very broad picture, but not necessarily give you skills, but still useful. I like to think of them as the books for your CTO, the person who used to program back in the day, but not anymore. Anyway, those two are good. You won't become a machine learning expert, but it will give you like some interesting high level about those fields. If you want to dive a bit into it, those are two good books, Nonsense and the 100-page machine learning book. They try to cover a lot of breadth with a bit of math. Worth reading. And finally, my personal favorite maybe is this one, which is a bit thicker, and it would carry you through the whole processing stages. It uses scikit-learn and then shows some neural nets. Now, mind you, the only resources I've shown so far is for people like me who are basically mathematically literate. There are a bunch of proper university textbooks about machine learning that might work better for you if you know the math very well. I'm not going to go into the names, but I'm assuming that your math knowledge is like kind of close to mine. You remember some basic stuff from the university, but you are in no way an expert. And those are the resources I found useful for me. And finally, the end game in your machine learning journey, in your machine learning journey, is something called Kaggle. Kaggle is a website where people upload datasets and then run competitions on who's going to do the best machine learning algorithm on this dataset. And the reason that it's amazing is because, one, it gives you data to play with, which is not that easy to come by. And two, when you get stuck, you can see what other people are doing, gather some inspiration, and then learn something. And then if you're very, very, very ambitious, you can even compete for money, although the competition is very, very intense. And anyway, that's about it. Do we have time for questions, Rado?
Sadly, we don't have time for questions, but that was pretty good for a first talk into here. So again, really big round of applause for Stefan. Woo!